Okay, welcome to 1.6 inverse functions and logarithms. So in this lecture, we have the following objectives. So we will discuss what is a one-to-one function. We'll discuss horizontal line test that's useful to check if the function is one-to-one. Our main objective is going to be inverse functions. And then we'll discuss logarithm functions, their properties, and we end with inverse functions, okay, trigonometric functions. Okay, so let's get started with one-to-one functions. What do I mean a function to be one-to-one? You remember, if you remember, we had a domain and a range of a function, and the domain, we thought domain as a set of children, and range set of mothers. And we said that one mother cannot have two, sorry, one child cannot have two mothers, right? So that's the condition to be a function. So now that if we assume further that every mother has at most one child, then it becomes one-to-one. Okay, so the one mother cannot have two children, or more than one children, then it becomes one-to-one. More formally, this is the definition from Thomas calculus. A function f of x is one-to-one on its domain if f of x1 is not equal to f of x2 whenever x1 is not equal to x2. Okay, so the definition might be confusing, but maybe you may remember the way I told you. To illustrate, let's give example. So let's first give an example which is one-to-one. So let's look at f of x, the linear function. Let's say the 2x plus 1, right? So basically, why this is one-to-one, right? Why this function is one-to-one? So whenever x1 is not equal to x2, I need to have f of x1 is not equal to f of x2. Okay. So or another way to show, so one-to-one. So another way to read this definition is one-to-one if the following, if f of x1 equal to f of x2, it can only happen if, so this is means if implies x1 is equal to x2. The only way that x1 and x2 are equal, sorry, f of x1 is equal to f of x2 is if x1 is equal to x2, if they are identical elements, right? So let's see. Let's start with f of x1 equal to f of x2. How can this happen, right? So what does this mean? This means from, so the function is 2x plus 1. It means 2x1 plus 1 is equal to 2x2 plus 1. But what does it mean? This means you can cancel once, you get 2x1 equal to 2x2. You can cancel 2 from both sides. This means x1 is equal to x2. So the only way that f of x1 is equal to f of x2 is if x1 is equal to x2, right? So that's the by definition. So this means, so the function f is one-to-one, 1-to-1. Sometimes we simply write like 1-1, 1-to-1. Okay. Okay, let me give an example which is not one-to-one. You might think, I mean, you can pause the video and think of a function which is not one-to-one. So let's for simplicity take x squared, right? It's not one-to-one. How do I show that it's one-to-one? I need to come up with x1 and x2 that are not equal. However, f of x1 is equal to f of x2. So, for example, take x1 is equal to 1, x2 is equal to -1. So I have two different children, right? 1 and -1. They are two different with names 1 and -1 if you like. But what is my f of x1? It's 1 squared. This is 1. What is my f of x2? It's minus 1 squared. It's also 1, right? So they're equal. So it means f of x1 is equal to f of x2. Well, those two things are not equal, but they're equal. So this invalidates the definition. So it means this function, this y is equal to f of x squared is not sorry is not 1-to-1. Okay, it's not. How do we check graphically? Well, graphically it's a horizontal line test. So that's the next objective, to a horizontal line test. You remember, to see if the function is well defined, if it is a function, we introduced the vertical line test, if you remember from previous lectures. And now this is a horizontal line test. This is useful to check if the function is 1-to-1. So what it says is the following. A function is 1-to-1 if and only if its graph intersects each horizontal line at most once. Okay, at most once. You remember our parabola? Here's our parabola. And let's apply this horizontal line test. So which means you sketch horizontal lines, okay? Basically. So what happens here? For this particular horizontal line, there is no intersection. So this is fine, right? Because I need to have at most once. However, once I go on x-axis, okay, it's also fine. Once I look at this particular one right here, right? It intersects twice. So this is contradicts to 1-to-1, right? So it means this is not 1-to-1, not 1-to-1. And if you look at the graph of any linear function, right? If you look at any graph of any linear function, let's say something like this, right? And if you apply the horizontals lines all the way, it intersects exactly once, right? Right? So this is okay. So this is 1-to-1. This graph is 1-to-1. Okay. Very nice. Okay, now inverse functions. Here's the definition. Suppose that f is 1-to-1. Okay, so this is needed. So we really need to have a 1-to-1 function in order to sort of invert the function, right? In order to take the inverse on its uncertain domain D, with range R. Then the inverse function, which is denoted by f to the superscript f superscript -1, right? Is defined by f inverse of b is equal to a if f of a is equal to b. And the domain, in this case, domain and range sort of interchanges. So the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the f inverse. Okay? Let's do an example. Let's say that I have a function which takes the following values. Here, when it's 1, let's say this is 2. When it's -1, let's say it's 5. When it's 0, it's 7. When it's 5, let's say it's 8, right? So it's kind of 1-to-1 because no two values go to the same, right? So let's say that it only had 4 points, right? So then what is f of inverse? So for example, what f inverse? F inverse of 2, right? Because now my range is 2. Here its range is 2, 5, 7, 8. But for the inverse, these are my domains. So I can ask the question like, what is my f of 2, right? What is it? Well, so to illustrate this formula, let me do it slowly. So f inverse of 2 is equal to a, if it's a, if f of a is equal to b, but b is 2. So what I do is I look at, I'm looking for a for which f of a becomes 2. So here, right? Let me pick different color. So here, I'm looking for a value x when f of x becomes 2. Well, I see that a must be, I see that a must be 1, right? So it means this value here is 1, right? So f inverse of 2 is 1. So it's the interchange roles. So now I think you see sort of, so you read, you see, to find f of x, you read from left to right, but to read the f inverse, we read from right to left, this table, right? So in particular, f inverse of 5, well, it's minus 1. F inverse of 7, it's 0. F inverse of 8, it is 5, right? Now, just as a side note, let me do something. Let's say that it's not one-to-one. Why? Just to illustrate why one-to-one is important. For example, let's say that I have another point, let's say 7. It also goes to 8, right? See? What would happen then? What would happen? Then, to compute my f inverse of 8, I need to look at for what? I need to look at for f of a that's equal to 8, right? But there are two values, right? 5 and 7, they both go to. So then this would mean my a would be, for a, I have two candidates, 5 and 7. This means my f inverse of 8 is 5 or 7, but it cannot have two different values, right? So that's bad. So this is bad. Okay? So this is not good. So this is not good. Because since my function has to be one-to-one in order to make sense of the inverse. Okay, how about the general situation, right? So in general, how do I find the inverse? Okay, let me again, for simplicity, let me first take a linear function. So f of x is equal to 2x, well, let's say 5, right? And the question is, find f inverse. Okay. So basically, what we know is, so f inverse of, so let me use the same notation. So f inverse of b, okay. F inverse of b is equal to a, if and only if f of a is equal to b, right? So what is my f of a? Well, this is, f of a is 2x plus 5, right? So this is 2a plus 5, 2a plus 5, right? So I need to find an a, right? I need to find a. So from here, I need to find a. So what is a? So 2a is equal to b minus 5. So a is equal to, you divide both sides by 2, you get b minus 5 divided by 2, right? So my f inverse of b is b minus 5 over 2. Or if you want to write in terms of x, so once you do all these manipulations, I mean, you can go back to your, because we started with x, right? So you may want to write f inverse of x. You replace everything by x, so it's x minus 5 divided by 2. By the way, remark is when you take f composite of f with f inverse, you need to get x. And similarly, the other way around, if you take the composite of f inverse with f, again, you need to get x. Okay, this is how you can check. Well, let's check for fun. Let's check. Here's my f of f inverse of x, right? If you remember, this is f of f inverse of x. Now, what is my f inverse? Well, I found it x minus 5 over 2. And now you remember your f. What was your f? Your f is 2x plus 5. So you, in place of x minus 5, sorry, in place of x, I have x minus 5 over 2. So you will have 2 times x minus 5 over 2 plus 5. So you cancel 2's, you get x minus 5 plus 5. 5's cancel, you get x, right? So indeed, we have x. So it kind of verifies that, yes, indeed, this is the thing that I found is indeed the inverse of 2x plus 5. One last thing, what happens if you have a function that's not one-to-one, right? Like if you pick a function f of x, let's say x squared. So then no inverse. This is not one-to-one, so not one-to-one. So no inverse, so no inverse. However, this is, I mean, this is a parabola. It's a nice function. It would be nice to take its inverse. So what you could do is you can restrict the domain where it's one-to-one, right? So for example, okay, it's not one-to-one. It's not one-to-one. So in its natural domain, it's not one-to-one, right? So it means so on minus 1 infinity to infinity, it's not one-to-one. However, but on if you restrict yourself to only positive numbers like 0 to infinite, then right, then y is equal to x squared is one-to-one. This is perfectly fine. And here you can take its inverse. So applying the same procedure, you need to solve for x. So here it means x is equal to square root of y. So then basically f inverse of x is, now you replace y by x, right? It's just square root of x. Okay? But we had to restrict ourselves to 0 to infinite. Okay, now let's discuss logarithmic functions. It's nothing but inverse of exponential function. So what is a logarithmic function? What base a, written in the form y is equal to log base a x, is the inverse of the base a exponential function. So we have this exponential function y is equal to a to the x, where a is positive and not 1. Then its inverse, the inverse of this, it becomes the log. How do we read this expression? There are two different ways to read this expression. So one way is log b, x can be pronounced as the logarithm of x to base b, or you can say the base b logarithm of x. Okay, base b logarithm of x. There are two very important special cases. So when a is equal to when a is equal to e, if you remember, this is the Euler number, which is very important in mathematics. So this is like 2.7182, etc. Right? It's a transcendental number if you know what it is. So in this case, we call it natural logarithm. So then we call this log e x. We also have a special notation. This is ln x. So this is called natural logarithm. Another common logarithm is when a is equal to 10, so base 10. Then we simply sometimes write like log, instead of writing log, this showing base 10, we simply ignore it and write like log x. So if this is the case, it means the base, if the base is not shown, it means it's base 10. This is the commonly accepted. Right. So for simplicity, for example, let's try to compute the log 10 to the, here, I don't know, let's say that 100, right? What is this? Let's say that if it's, let's call it y, but then you remember its inverse, so you realize that this is like 100 is equal to 10 to the y. How come 100 is equal to 10 to the y? It's possible if y is equal to 2, right? So it means your logarithm, base 10 logarithm of 100 is simply 2, right? This is how you find the logarithms. You go back to the exponential function uh, because it's an inverse, and then find the values there. Okay, properties of logarithms. Very interesting. It has very interesting properties, as you probably know. The product rule. Well, here it's given for the ln, for the natural logarithm, but the similar things apply. The same apply for any logarithm with any base. So ln of b times x is ln of b plus ln of x. Ln of b over x is ln b minus ln of x. Ln 1 over x is minus ln x. I think this is you can get it from previous one. And then ln x to the power r. So you see this power r goes to the front, right? So these are nice rules of logarithm when it comes to do some algebraic manipulations. Okay, what else? Because a to the x is the inverse, or yeah, it's the inverse of base a logarithm of x. Because of this, you have such properties. So I'm not going to prove it. So a to the power log a x is equal to x, or base a log a to the x is x, etc., right? Uh, so some examples could be like, by the way, log base a of base a log a is always 1. I think you probably know, or you can also see it from here when x equal to 1, right? Right. This is also comes from the previous ones, etc. Right. What else? Every exponent function is a power of the exponent. Yes. So the reason why sort of we only saw these properties is because you can realize other exponents with base e, right? So a to the x, you can always write as e to the x ln a, right? Why it's the case? So it's coming from these properties. So let me start with e to the x ln a. But what is it? From this power rule, right? From this power rule, I can take r to the power. So here I can take this x to the power, so I can write it as e to the ln a to the x, right? Ln a to the x, right? And then use this particular property when you have a and a here. So here it's ln means e here, right? So it becomes a to the x, right? A to the x, and that's what we want. One last thing about the logarithm is change of base formula. So base a logarithm of x can be written as ln of x divided by ln of a, right? Or in fact, similarly, you can also do base a logarithm of x. You can write, in fact, in any base b x over log base b log of a, right? So there is nothing special about ln here. You can do this. So now let's discuss taking inverse of trigonometric functions, right? Well, we have one problem with trigonometric functions. They are not one-to-one, right? So let's take example of a sine function. sine of x. If you remember the graph of the sine, it's periodic, right? It continues as such, right? So here it's 0 whenever it's 0, and it's 0 at pi, it's 0 at negative pi, it achieves the maximum at pi over 2, right? This is 1. Here it's minus 1 at minus pi over 2, etc. Now the problem here is, if you remember how you check for the one-to-oneness, well, if you look at the horizontal, you pick any horizontal line, it not only intersects, so to be one-to-one, it needs to intersect at most once, right? Right, so at most once. But here it intersects infinitely many times, right? So it intersects infinitely many times. So function, so it is not, so sine is not one-to-one, so not one-to-one, so not one-to-one on R, right? If I look at its natural domain, which is R, the whole of real numbers, then it's not. Well, but trigonometric functions are important. We really need to know their inverses. So what we do, we have to restrict the domain, right? We have to make it smaller so that it becomes one-to-one. So what I can do is here, for example, if I restrict myself to this domain, so restrict to minus pi over 2 to pi over 2, right? Then my graph, okay, let me resketch it. So here's my minus pi over 2. Here's my pi over 2. Somewhere it's 1, here it's 1, etc. So here's minus 1, here's 1. So here now I'm perfectly fine with horizontal, right? I'm perfectly fine with horizontals. If I sketch somewhere here, it never intersects. If I sketch here, it only intersects once, etc. Right? So I don't have any problem with horizontal lines. So then restrict to then sine of x is 1-to-1. So it has inverse, right? So it has inverse. We call it, what do we call it? Call it arc sine, right? Sometimes we call it arc sine, etc. By the way, what does it mean to take the inverse, right? How does it reflect? How do you sketch the inverse? Well, sketching inverse is, it's because taking inverse means the flipping the range and the domain. So it means the same for the graph. It means you sort of flip the graph. But how do you flip it? You need to flip it across the y equal to x line. So you have to reflect it. So let me show you. Let's pick green. So you take this. This is y equal to x. So you reflect it. Okay. So inverse means inverse is reflection. Reflection along y is equal to x line. Right? Think of this line as sort of a mirror, and then you try to reflect the graph along this line. So let me take black. So if you reflect this arc, it becomes something like this, right? And here it becomes something like this, right? So that's the graph of arc sine of x. Remember, arc sine of x is the inverse, right? It's inverse of x. Yeah, I don't want to do it for all of the other trig functions, so let me show the table. Okay, So this is sort of what we did. So this is the sine. So for sine functions, when you want to take inverse, you have to restrict yourself to this domain. So you need to remember these domains. This becomes important. For cosine, we restrict from 0 to pi. For tangent, we restrict from minus pi half to pi half. However, we do not include the endpoints because these are undefined, right? Tangent is not undefined there. For cotangent, it's 0 pi. For secant, it's 0 pi union pi, 0 pi half. It's 0 pi excluded pi half. And for cosecant, it's minus pi half to pi half. Again, you exclude 0, right? Because these are, you're dividing the trig functions there. So let's do a few examples and I will stop then. So let's say that I want to compute. Let's say that I want to compute arc sine of 1 over 2, right? What is this? Well, we need to look at for which x I have 1 over 2. But what was my domain for arc sine, if you remember? So this is minus pi half to pi half. So in this domain, I need to look at x that gives me 1 half. Well, it's the 30 degree, right? We know that sine 30 degree, which is pi over 6, is equal to 1 over 2, right? So this means my arc sine of 1 half is equal to uh, yeah, pi half, pi over 6. Okay, let's do something. Let's compute arc cosine. Arc cosine. I don't know, 1 half also, right? So this means we are looking for cosine of x equal to 1 half, but what was the range here? It's from 0 to pi, right? So in this case, we see that x must be 60 degree, right? So this is pi over 3. So it means arc cosine of 1 half is pi over 3, etc. Okay, so you only need to go back to the original trig function to compute the inverse. So one quotient, one quotient is the following. Do not get confused. So sine inverse of x, it's not the same as sine x inverse. They are not the same. Because sine x to the power minus 1, this is like power, right? This is the power, so it means 1 over sine of x. So that's different thing, right? This is cosecant, right? Cosecant of x, if I remember right. But sine inverse of x, so this is arc sine. Arc sine. Okay, so they are two different things. So just be careful with the notations.